Welcome to Chapter 2, Part 2 of Anatomy Physiology 1. So as we left off, we had been talking about protons, neutrons, and electrons. And you cannot change the number of protons because you'll change the identity of the atom itself. It will become a completely different element. You can change the number of neutrons because they're neutral. They don't have a charge on them. So if you have a few more or a few less, it's usually okay. But if you go overboard and you have a few too many neutrons or a few not enough neutrons, then you make the isotope into a radioactive isotope, and the nucleus will become unstable, and you'll have to wait over a period of time until it equilibrates, it throws out energy, it throws out particles, and now it's no longer radioactive. So the person who gets credit for this and the Nobel Prize for it was Madame Curie. I think everyone's heard of her. First woman ever to get a Nobel Prize. Unfortunately, in discovering radioactivity, it also killed her. So she died at the age of 67 from radiation poisoning. I find it amazing that I have lived longer than Madame Curie lived. But then I didn't play with as much isotopes as she did. I'm just kind of an aging hippie, I guess. But one of the things that I don't agree with, don't think is a good idea, is to try recreational drugs. I've just not seen that work out very well. So I can blow my mind and freak myself out without having to resort to any kind of chemicals. I could just think of something like this particular thing that I found on the internet. We are made of stardust. So if you think about all the atoms that are in the periodic table, they came from somewhere. They came from other planets. They came from a passing comet or one that crashed into the Earth. The different atoms are taken up by animals, or taken up by plants, and then we eat the animals, we eat the plants, and now their atoms are part of us. They become part of the atoms within us. When we pass on, some of us goes into the soil, some of us goes into the air, and our atoms are recycled. So if you stop and think about where all the atoms in your body came from, some of them came from streams, some of them came from rocks that dissolved when the rains came. It's amazing to think that you're made of recycled atoms and you're going to go and be recycled again. The next thing we're going to talk about is chemical bonding. Your book does ions and ionizations and electrolytes first, and then it goes into bonding, but it doesn't make any sense to me to do it in that order. So since I'm the boss of this video, we're going to talk about bonding. So there's basically two types of bonding, and then there's two kinds of attraction that they call bonding, but isn't actually bonding by the technical definition. So one of the things that I told you, and it's a true story, is the number of protons and the number of electrons have to match. So if you've got 8 protons, you have to have 8 electrons to balance out the negative and the positive charges. Otherwise, you're going to end up with a molecule or an atom that has more positive charges because it has more protons, or more negative charges because it has more electrons. So we don't want that situation to occur usually. So here's a paradox. One of the goals of every atom on the periodic table, with the exception of the far right column, wants to either get rid of all the electrons in its outer energy level, or it wants to take on enough electrons to fill its outer energy level. Well, so the paradox is we can't do that, because if you give up electrons or take on electrons, you're going to have a charge. And we just said that we don't want that to happen. So when you bond, you share electrons. So you don't give up your electrons, you just kind of share with somebody who needs one. So let's look at the periodic table and see if we can figure out what I'm talking about. Let's look at sodium. It's in column 1. So we know it has 1 electron in its outer energy level. So we have something called the octet rule, and sodium would either want to give up the 1 electron, so it's emptied out its outer energy level, or it would want to take on 7 more electrons to fill up its outer energy level. So obviously it's a lot easier to give up that 1 electron than it would be to go out and try to find 7 electrons that some other atom doesn't need. All right, let's go all the way over here to this column right here. This is column 7. So all of these have 7 available electrons in their outer energy level. So if they wanted to fulfill the octet rule, they would, instead of giving up 7 electrons that they have in their outer energy level, they go looking for 1. So they would go looking for 1. Now, if you remember, I just said sodium has 1 to give up, and chlorine is looking for 1. So if I put sodium and chlorine close together, they're going to share sodium's outer electron. So now both of them have fulfilled the octet rule. Sodium has lent its electron to chlorine, and chlorine has borrowed the electron from sodium. And so it has 8 electrons, and sodium has none in its outer energy level. So everybody's happy. Well, this happens to be sodium chloride, and you and I call it just common table salt, the stuff that's in the salt shaker right next to the pepper shaker. Now here's an interesting thing. I'm going to pause just for a second to talk about this, because sodium, the element sodium, is extremely explosive. And back a long time ago, of course, students love things that blow up. So chemistry teachers would go and get a little piece of sodium, and they walk across the room, and they'd be talking about sodium, and then they'd drop the piece of sodium in a garbage can, and it would blow up. And it was great. The kids loved it. But unfortunately, if you had a teacher like me that's long-winded and gets off topic and thinks of, oh, wait a minute, I have to tell you one more really cool thing, they would end up blowing their hand off, or if they were holding it in front of their face, blinding themselves when it exploded. So they don't allow us to have sodium in our classroom anymore. So you guys, this whole generation is lost out on watching sodium explode. And it's pretty dramatic. You can go on YouTube and watch videos of sodium exploding. Truly amazing. Chlorine, we all know, is a deadly gas. You bubble it in your swimming pool and it kills off anything that's in your swimming pool. So this is nice. You know that if you try to get in the swimming pool too quickly after you put the chlorine gas in there, it stings your eyes and burns your nose, and it's really hard to get in there. If you were silly enough to jump in the pool yourself right after they had added the chlorine, which unfortunately happened to a friend of mine, some kids thought, oh, I don't want to wait, and they went and jumped in the pool, and it killed them. So chlorine can kill big things too, but usually we wait until most of it has gone off into the air and left as a gas. So there's not enough remaining in the water to hurt us anymore. So here you take a highly explosive thing, you take a very deadly poisonous gas, and once they start sharing an electron, fulfilling the octet rule, they become just regular old food, sodium chloride, which we have in all of our food. So unless you happen to have high blood pressure and you can't pee out your sodium, it's not dangerous to us. So we eat it on our pretzels and we put it in our French fries and so on. So by sharing an electron, you change the properties of each of the individual elements. So it's no longer dangerous. So that's kind of an interesting concept. So everything goes along just fine with salt, sodium chloride, unless you put it in water. When you put it in water, the water molecules will actually get in between the sodium and between the chlorine and push them apart. Now, because we have an unequal sharing of electrons, so sodium only had 1 and chlorine had 7. That's an unequal sharing. So what's going to happen when the water gets between them and pushes them apart? Chlorine's going to take off and keep the electron that should have stayed with the sodium. So we call an unequal bonding like that an ionic bond, because once you add water and you separate the two atoms, now you have ions. Now the sodium lost an electron, so it has 1 extra proton in the nucleus, so it's going to be overall positively charged. So if we were to write this down and let you know that sodium is in the ionized state, or it is an ion, you would write capital N, little a, and a plus sign. And that plus sign lets you know that it is positively charged because it lost its electron. In the case of the chlorine, because it stole an electron, it has an extra electron and it is negatively charged. So we would write it capital C, little l, and then a negative sign to let people know that this is an ion. Now, it doesn't go back to being the sodium explosive and the chlorine a dangerous gas, because now it's in its ion form. And actually, some of the things we actually need to be in their ionized form or in their ion form inside of our bodies in order to make our brain work, in order to make our muscles work, and our heart beat. And sodium is one of the things that we actually need to have in its ion form. And potassium is another one that we need to be in its ion form. So not all ions are bad. But in general, you don't want charged particles running around in your body. I use the example of water to tell you about how you can make an ion out of sodium and chlorine, but there are other things that you can do that will cause atoms to become ions. Ionizing radiation is a classic example. If you use X-rays, if you use gamma radiation, if you're around hanging out in a basement where they have a high level of radioactive radon in the air, all these things can cause your molecules to ionize, to separate, and one of the atoms goes off with the other one's electrons. So then they both go off as charged particles. So ionization is anything that can cause the electrons to take off in the wrong direction with a wrong atom. If a particle has a net negative charge, for example, chlorine, it stole the electron from sodium, so it has an extra electron, we're going to call that an anion, an anion. And a particle that has a positive charge, because it lost its electron, we're going to call a cation. Cation. So here's a little thing to help you remember that. It is positively charged. Cat. Positively charged. Here's a picture showing all of the stuff I've been talking about up to date. And so let me walk you through this a little bit. Here's sodium, so you can see the protons and the neutrons in the middle. You have 2 electrons in the first energy level, 8 electrons in the next energy level, and then you've got 1 extra electron out in the third energy level. Here is chlorine. Here's the protons, neutrons, 2 electrons, 8 electrons, and then 7 more for a total of 17. So this atom is going to share an electron with this one. So it shows you, there it goes. But they're going to stay together. So they're bonded together because they're sharing an electron. Sodium doesn't want to give it up, and chlorine wants it, so it lets sodium tag along. But whatever ionizing event happens, if you pull these two away, chlorine's going to take off with the electron, and sodium's going to be left without one of its electrons, so it'll have an overall positive charge. Now I'm going to tell you something else that sounds like a paradox, because you have been taught all your life, do not get into the bathtub and drop, say, a hair dryer or anything that has electricity running through it. People used to drop radios in. Of course, now we have phones, we drop them in and they die. But in the times where people would drop in a hair dryer, or they would drop their radio in that was plugged into the wall, it would electrocute them and they would die. So they always say don't have electrical things. And in fact, there's a ruling now, and anytime you have a place that's got water, like in your kitchen or in your bathroom, you have to have special plug-ins to keep you from getting electrocuted in the chance that you drop the electric thing in water and you electrocute yourself. So we actually are protecting you from that. But now here's the paradox. Water does not conduct electricity. You're like, well, now the lady's lost her mind, because obviously water does conduct electricity because people get electrocuted in the bathtub. Well, in order for that to happen, you've got to have ions in the water. So you have to have a little salt in there, or a little chlorine in there. If you stop and think about it, why are you taking that bath anyway? Because you're covered with sweat. So you've been perspiring salt. If you've ever tasted sweat, it's very, very salty. So once you get in the water, all of the ions that are on your body wash off into the water, and now the water can conduct electricity. So you're the one that made it be able to conduct electricity. Also, most of us don't have pure water in our house. The water that comes out of the tap has fluorine, has chlorine, has all kinds of other things in it that you probably wouldn't want to think about, because they can't get all the stuff out when they clean the water. So what comes in your house has a certain amount of things that we don't usually talk about. When we talked about homeostasis, one of the things that you have to keep in balance in your body are your electrolytes. You cannot have too much sodium. You cannot have too much potassium. You cannot have too much chlorine, because it can cause you to go into a coma, or it could stop your heart. And I think we mentioned earlier that lethal injections, they just inject you with potassium. So now you have way too much potassium. Your heart can't beat, and it's supposedly a humane way to die. That's why we put our dogs and cats and other pets to sleep using potassium. With the exception of sodium and potassium, which we need to become ions, most of the other things that are ionized or become ions, it can be dangerous to us. We call these free radicals. So it is a particle that has the wrong number of electrons. It could be a molecule, it could be an atom. They occur normally in your body, but some people do unhealthy things, so they make more free radicals than other people. If these free radicals are allowed to do whatever it is they want to do in your body, it can trigger cancer, it can alter your DNA, it can kill your heart, and it can cause premature aging. So I know you've seen people and you're like, whoa, look at that person, they're like 60 or 70 years old, And then they say, yeah, this is Mary. She's 35 years old. And you're sitting there going, what? Of course, smoking will do that too. It ages you prematurely. But anyway, so free radicals are not a good thing. We need to get those electrons off of the ones that have too many and put them on the ones that don't have enough so that everybody is neutral. Because that's what we need, everything to be neutral. So what we can do to stop these free radicals from attacking parts of our body is to take antioxidants. So there are certain things that you can eat. Vitamin C is one of the most famous of the antioxidants that you can have. Drinking orange juice or taking vitamin C pills. Your body makes an enzyme that its specific job is to be an antioxidant and fix ions that are running around as a free radical. Here are some of the other things that are antioxidants: selenium, vitamin E, the carotenoids. So these are things that you eat, and they're going to take care of your free radicals. And a lot of people take supplemental vitamin C and supplemental vitamin E, and you can take selenium supplements too. So if you go in any drugstore, grocery store, or whatever, and go over to their supplement aisle, you're going to find antioxidants over there. So let's go back to our periodic table and let's look at something from the second column. And we're looking at magnesium, and it has 2 electrons. So if it was looking for an atom to give or share its 2 electrons with, because it's easier to get rid of 2 than it is to go find 6. So let's go over to column 6, and we're going to find oxygen and sulfur, and oh, there's selenium. Isn't that interesting right there? So these atoms right here have 6 electrons, and they're looking for 2. So it's going to work out so nicely if these guys over here and these guys over here get together. So you can mix the magnesium with the oxygen, and both of them will bond. And I saw this and I couldn't resist. I like memes. I like jokes. And I especially like it when you're in on the joke. You're in on the secret. So somebody said, did you hear oxygen and magnesium got together? So we know that they're sharing electrons. And this one says, OMG. There's your oxygen and there's your magnesium. So let's look at another thing. So here's oxygen, it has 6 and it's looking for 2 electrons. So we know that it can combine with anything in column 2. But how about column 1? So oxygen needs 2 electrons. Hydrogen would like to either get 1 electron or give up an electron. So it can go over and it can bond with oxygen. And the hydrogen is happy because it gave up its electron. It's sharing it with oxygen. But oxygen is not happy because it went from 6 to 7 electrons, but it needs 1 more to fulfill the octet rule and fill its outer energy level. So it can go and have another hydrogen bond to the oxygen. So now you have 2 hydrogens and 1 oxygen, and of course we call that water. H2O. So that little subscript 2 means there's 2 hydrogens and 1 oxygen. So there's another way that you can bond. And if you look at carbon, carbon has 4 electrons. So it can give up 4 or it can take on 4. So pretty much carbon will bond with anything on the periodic table, with the exception of this column right here. These are called the noble gases, and they're called that because their outer energy level is already full. So most textbooks will say that helium, neon, argon, krypton, xenon, radon do not bond with anything. But of course, anytime you say something like that, this never happens, then somebody's going to go, well, wait a minute, I actually have seen fluorine and xenon get together. But it's rare. So these guys already have their outer energy level full, and they're called noble gases because they're stuck up and don't have anything to do with all the other atoms on the periodic table. Now I want to show you something before I forget. If you look at these different elements down here, you're going to see that some of them are in black and some of them are in I have this pop-up that keeps coming up on my computer, and I apologize for that. These, sorry, I don't know how to make that stop. These at the bottom from 93 over are not grayed out, but they're just an outline. So they aren't real atoms. They do not exist on Earth, but they have been made in a laboratory, and so people say, well, I made it and it stayed together for 10,000ths of a second, so I get to name it as a new atom. So I call them fake atoms. So all the way through to uranium, which is 92, those are real atoms, and the others are made in a laboratory. So this is, they don't mention, well, actually they do mention Ikea. One of the things that Ikea is famous for is they give you stuff that is not assembled. So you have to assemble it. So in this case, he thinks he's getting water, but instead he's getting 2 tanks of hydrogen and 1 tank of oxygen, and they're going to combine together and make water for him. And you get a little bucket, and once the gases have united. So isn't that interesting that hydrogen is a gas and oxygen is a gas, but yet when you put them together and they're sharing electrons, it ends up making water, and at room temperature is liquid. Here is a picture of what water looks like. So you have oxygen here, and you've got those electrons out here, and here it is sharing one with this hydrogen and with this hydrogen. So to me it looks like Mickey Mouse ears. See, can you kind of see Mickey Mouse? There's his head, there's his ears. Now interestingly enough, the hydrogen, because its electron is down here close to the oxygen, because oxygen is borrowing its electron, and this one is borrowing its electron. If you were to come in space towards this hydrogen, you're going to be coming towards a proton. So this is positively charged. This is positively charged. So this whole side of this molecule is positively charged. And if you come at the molecule from this side, from the oxygen side, then you have all of those electrons. So remember it had 6 electrons, and it borrowed 2 from hydrogen. So here are the 6 electrons. So if you come at the molecule from this direction, it is negatively charged. Now this is one of the things that I disagree with, but I'm not the boss of the world, and I'm certainly not the boss of the chemical world. They call this attraction that occurs between, here's a water molecule, and its hydrogen will be attracted to this oxygen. It can't bond, it can't share electrons because the electrons already shared with this one. But opposites attract, so this is a positively charged nucleus, and here's a negatively charged outer energy level, and they're going to be attracted to each other. So an example that I can give you that's kind of like that, if you've ever taken a balloon and rubbed it on your hair, then you get a static charge on it. And you can stick the balloon on somebody else's hair, or you can stick it on the wall, or you can stick it to another balloon. So you have an attractive force. but it is a very weak attractive force. All you have to do is just flick the balloon with your finger and it'll go floating off. You've broken the attraction. So in the case of water, the attraction's pretty strong because one hydrogen can attract to this oxygen and this hydrogen can attract to another oxygen, and you're going to get what we call surface tension on water. So if you look at water, you weigh too much, so you can't walk on water. But if you look, there are bugs. They're out there just walking along on the water. And you can actually see where the water dimples, where they put their foot and they actually compress the water. You can see where their foot presses down in it. So it's kind of cool. But they call this hydrogen bonding. And if I got to change it, I would call it hydrogen attraction or opposites attracting. But I wouldn't call it bonding because bonding is where you actually share electrons. So, but anyway, that's just me being a Karen and being grumpy. So since I can't stop people from calling it hydrogen bonding, I can make fun of it. So here's bond, hydrogen bond. So it's very important that you do understand hydrogen bonding, the attraction between electrons and hydrogen, which is a naked proton, positively charged, because this is going to cause fluids to move in your body. It's going to be important for osmosis. It's going to be important for dissolving things, for making ions. So there's a lot of things that are important about hydrogen bonding. When we make big proteins, if certain parts of the protein are attracted to other parts, then the protein will fold up so that the positively charged hydrogens are close to negatively charged things like oxygen. So it's going to influence the shape of molecules. So hydrogen bonding is extremely important. If we were doing a biology class, it would be what causes the water to go up from the roots of a tree or a plant up to the leaves, because the water is attracted to each other. And so if you can pull one of them, it's like a daisy chain and it'll pull the others that are hydrogen bonded to it. The other kind of true bond that we need to talk about is a covalent bond. And in this one, you have a more or less equal sharing of electrons. So other than the things in the first column combining with the things in the seventh column, most of the other bonding tends to be covalent bonding. So how do you know if you have an ionic bond? Well, there's a couple of ways that you can look at it. One of them is if you put it in water, does it conduct electricity? That's one way you can tell. When you put the two atoms together, does it make a salt? So ionic bonds form salts. So table salt. Some people can't have salt because their kidneys don't work right. So they have what they call no salt, or they have potassium chloride instead of sodium chloride. So here's some words that you guys need to know the definition of. When they talk about a molecule, they're talking about atoms that are put together by sharing electrons or united by a chemical bond. A compound is a molecule made of two or more different elements. And you're like, wait a minute, wasn't that pretty much what we just set up here? Well, let's give you an example of one that is a molecule but is not a compound. If you think about hydrogen, it's got one electron, so it can either give up one or take on one. Well, if you have two hydrogens and put them together, they'll stick together. So now they have two electrons between them. So one of them sharing with the other, and they both fulfill the octet rule. So in that case, you have two atoms that are united by sharing of electron. but it's not a compound because it's not two different atoms. All right, you catch that difference there? And if you take a chemistry class, you'll find there are 7 atoms on the periodic table that never occur as a single atom. They never occur alone. Hydrogen is one of them. So anytime you have hydrogen, you can have another hydrogen attached to it or some other atom. But you're never going to find hydrogen by itself. And anything in the 7th column, fluorine, chlorine, bromine, iodine, any of those, they always hang out with another molecule of chlorine, fluorine, bromine, or some other atom. So you're never going to find fluorine by itself. You're never going to find chlorine by itself. And another one is nitrogen and oxygen. So those are the 7 atoms that are never, ever found alone. Of course, the minute I say that, somebody's going to go, well, now, in this case. But to all intents and purposes, you never find them alone. So if you need to know that for a chemistry class, the abbreviation is Brinkelhoff. If you write down Brinkelhoff, that's the 7 diatomic atoms, the ones that never occur by themselves. Or you can just remember hydrogen, oxygen, nitrogen, and all of the ones in column 7. So we write down compounds by giving them a molecular formula, and it's also important to know the structural formula. So again, you know I got to have a cartoon. And here's the one I found. Here is carbon. It has 4 electrons. So it's going to share 2 of them with oxygen. Remember, oxygen's looking for 2. It's got 6. It wants 2 more. So it's going to borrow 2 from carbon. And carbon still has 2 more, so it's going to give 1 to hydrogen. It's going to give another one to hydrogen. If you have a spare electron, it's always easy to give it to hydrogen. So you're going to find hydrogen bonded to just about everything. So get used to seeing that. And when you put carbon plus oxygen and 2 hydrogen, it's called formaldehyde. Now, you guys are probably young enough, you don't even know what formaldehyde is. But back in the day, when you can talk to your parents about it or your grandparents about it, and they go, oh, I know formaldehyde. It is a very strong chemical that will keep anything from growing. So if you have a mouse and you want to preserve it, you can put it in formaldehyde. And you can take it back out of the formaldehyde 10 years from now, and it'll be just fine. So in gross anatomy, when people donate their body to science and medical students take the bodies out and look at the internal organs of a real human being who's passed on, a lot of times they keep the bodies preserved in formaldehyde. So there's the formula for formaldehyde. And one of the things that I heard, that if you leave your soft drinks, the ones that have artificial sweeteners in them, if you leave them out in the car and they get really hot, a lot of times they can turn into formaldehyde. So not enough to kill you, but enough to make your soft drink taste funny. So I don't know if you've ever noticed that you've left a drink out in the car for a long, long period of time, and then you open up the can to drink it, and you're like, this just does not taste correct. So anyway, and then of course somebody made a joke, if you dress up the formal formaldehyde with some beach clothes, then you have casualdehyde. Ha ha ha. And 2 helium atoms were acting funny. Hee hee. So here's a little table that your textbook put together to show you. You can take the exact same atoms and put them together in a different way, and you get different things. For example, if you take 2 carbons and, let's see, 2, 4, 6 hydrogens, and 1 oxygen, you can make ethanol. And so you and I would call this vodka. This is vodka, ethanol, and you can drink it. And then you can take the exact same 2 carbons, 6 hydrogens, and 1 oxygen, rearrange it like this, put the oxygen instead of over here, put the oxygen in the middle, and now you've made ethyl ether. And you know that ether is what they use to put you to sleep with, or they used to use it. They don't use ether except for in thrillers. They'll make ether and they'll kidnap someone by putting a cloth soaked in ether over their nose until they fall asleep. So they used to do surgery this way with ether. So depending on how you put the atoms together, you're going to get different effects. You're going to get something that's completely different, something that'll make you happy if you drink, vodka, or put you to sleep in the case of ether. Another thing that happens when you put atoms together differently, you can have right-handed molecules and left-handed molecules. So if you shine a light at a molecule and the light turns in one direction, then we say it is an L isotope. And if it is D, if it's dextrorotatory and it bends the light in the other direction, then we call it a D. So they took Samuel L. Jackson, and then they said, oh, and this is Samuel D. Jackson. Well, if you try to take this picture, so this is Samuel L. Jackson, and superimpose it on top of this one, it won't fit because he's turned this direction in this one, and he's turned this direction in this one. So it won't fit. Another example that they usually use is take your hand and put one hand out and then put your palm on the back of your other hand, and you'll see that your thumbs are on opposite sides. So those are isomers of each other. Your hands are isomers. So they go in a different direction. So now we're getting way out of the realm of stuff that we should be talking about in an introductory anatomy class. But it's important to know because bacteria are going to be making their proteins to rotate light in one direction, and we make ours to rotate in the other direction. And why is this important? Because if I want to stop the growth of a bacteria, I can keep them from making proteins that rotate in that direction without interfering with me, because I make proteins that rotate in the opposite direction that the bacteria does. So it's one of the bases of how to make antibiotics. So I wanted to throw that in there. So I'm going to summarize here because there's 3 words that students get confused about, especially if they've never had chemistry before. This is all running together in their head, and they're like, I don't even know what that woman is talking about. So isomers are molecules that have the exact same atoms, but they're arranged differently in space. The exact same atoms, but they're arranged differently in space. Those are called isomers. Ions, also starts with I, ions, is an atom that has the wrong number of electrons. It either it's missing some or it has too many. So an ion is an atom that has the wrong number of electrons. And it's going to be looking to fix that. It's either going to give up the extra electrons or go and find electrons from someplace else to make it neutral again. So they're constantly seeking to become neutral. And then the word isotope. It also starts with I. So we have ion, isomer, and isotope, all starting with an I. And remember, an isotope is something that has a different number of neutrons. It's the same atom, but has a different number of neutrons. So it's either lighter than most of the other atoms or heavier than most of the other atoms. But it is still the same atom. So if it's a hydrogen, it's still a hydrogen. If it's a nitrogen, it's still a nitrogen. Okay? So think whatever it takes for you to get ions, isotopes, and isomers straight in your head, work on it. All right, this looks like a whole bunch of something that's going to be really, really complicated. But if you want to find out how much one molecule weighs, just add the weight of each of the atoms. That's it. So in the case of oxygen, it weighs 16. If you add two hydrogens, they each weigh 1. So a molecule of water, H2O, is going to weigh 18. So 16 of the weight comes from the oxygen, and 1 comes from each of the hydrogens, so that you end up with a total of 18. Here is glucose, who everybody else in the world calls dextrose. It has 6 carbons, 12 hydrogens, and 6 oxygens. So carbon weighs 12, and if you have 6 of them, they put 66 instead of 6. That's funny. So that's an error right there. I wonder if I can get rid of that. Nope. Well, when I tried to fix the slide, I lost it. So what I was doing was I was taking 6 carbons, which weigh 12 each, multiplying that out, and 12 hydrogens, which weigh 1 each. So 12 times 1 is 12. And if you add up all the carbons, hydrogens, and oxygens, then one molecule of sugar, of glucose, or dextrose, weighs 180 AMU. So if you were going to go into pharmacy, you'd need to know stuff like that, because you're going to have to be able to figure out the molecular weight of different compounds. And you're going to need, especially if you're going to be a formulating pharmacist, where you actually are a compounding pharmacist, where you actually make the medicines. You don't just buy pills ready-made. You actually have to put them together. You have to be able to know how to weigh them out and stuff like that. So again, way out of the range of what we need to know for anatomy class. Van der Waals forces, this is where atoms are punching each other and bouncing off of each other. They're constantly in motion. So it is a very, very weak attraction. So at least they don't call it the Van der Waals bonding. It's just a force as these things bump into each other. So if you were to look at water moving, you can't really watch the water move, but what you could do is sprinkle a little pepper or something that would float on the water and watch it move around. So you can see that things are constantly in motion. They don't sit still. So why do we even talk about the Van der Waals forces? Because they help us fold our proteins and keep our proteins folded. And if the proteins aren't folded right, especially enzymes, they won't work. They want to point out there's a difference between a mixture and a compound. So a compound has been chemically bonded. A molecule is chemically bonded. So unless you do something like ionizing radiation or you use enzymes or something of that nature, then you're not going to disrupt that molecule. But in the case of a mixture, they're not combined chemically. They're not sharing electrons, they don't have ionic bonds, they don't have covalent bonds, they don't have hydrogen bonds. So you can get these things apart. For example, I mentioned pepper. If you put pepper on your substance, let's say we put it in with sugar. All I have to do is put it in water and the pepper will just float up and the sugar will dissolve into the water. So I can separate the pepper from the sugar. They are not chemically united. They're not sharing electrons. So it's a mixture of sugar and salt. or a mixture of pepper and salt. So mixtures can be separated back out because they're not sharing electrons. Water is super important because it's polar. It's got that positive end of where the Mickey Mouse ears are, the hydrogens, and it's positive, and the other end is negative. So it's polar, and we're going to be talking about the polarity of water in other chapters. And most of your body weight is water. So women tend to have less water than guys. Older people, people who are fat, all of these things are going to influence how much of your body weight is water and how much is other things. So anywhere from 50 to 70% of your body is water. So water is going to be important because some things can dissolve in water and some things can't. So if you stop and think, well, what can't dissolve in water? Fats, lipids, they can't dissolve in water. So that's going to be important when we talk about hormones because some of your hormones are fats. And so they're not going to be able to dissolve in the water and be carried in the bloodstream, where others can dissolve and be carried along in water. Cohesion, holding things together, the water is attracted. So surface tension is an example of this. Adhesion, you're going to find the water sticking to the walls of the blood vessels. If you sweat, the water sticks to your skin. You ever think about that? So it has to be really heavy before it actually starts dripping off your face. But look at somebody when they're sweating and they're glistening because the water is attracted to their skin. So adhesions, like a Band-Aid is an adhesive. It sticks to you if you put a Band-Aid on. Chemical reactivity. We talked about sodium and chlorine getting together and making table salt, and they just hang out, everything's cool. And then you put a little water on it, and all of a sudden you've turned it into ions. They're charged particles, and they can conduct electricity, and they can cause chemical reactions to occur. And in the case of your brain, your heart, and your muscles, it causes them to work. So water, super important. Thermal stability. If you are really, really cold, then you're going to pull the heat into the core of your body by bringing the blood vessels closed on the outside of your body and opening the ones on the inside of your body. So now your core stays nice and warm, but you may lose your fingers and toes to frostbite, but at least you're not dead. So thermal stability, it helps maintain our body temperature. Two terms on this slide I'd like for you to know are hydrophilic, or water-loving, and hydrophobic, which means it will try to get away from the water. And this is going to be important when we get in the next chapter. So we're going to talk about hydrophobic molecules. I like this picture. It reminds me of bullying on the molecular level. If you had that sodium and you had that chlorine and you add water to it, here's what happens. These water molecules are going to put their negative end towards the sodium, and they're actually going to make a circle around it. You can only see the flat circle, but it's actually a sphere all around it. It's called a hydration sphere. And it can't get back over to the chlorine. It can't get back to its electron that it lost. In the case of the chlorine, it's sitting here with an extra electron, so it's negatively charged. So the positive ends of the water molecules are going to encircle it. So they're preventing these two from getting back together again. So I just thought that was interesting. Now, one of the things that is very important to know about water is it can ionize into hydrogen with the positive charge because it left its electron over there with oxygen. And the rest of the water molecule, which is OH, with a negative charge. So we actually have a name for this. This is called a hydroxyl ion. So let's see if you guys can get this joke. Here is the hydroxyl, the OH part of the water molecule. And here's somebody talking to their therapist. I have a fear of hydroxyl groups. And the therapist says, oh, which is a hydroxyl group, OH. And then the person freaks out because they're afraid of hydroxyl groups. And the therapist just introduced one into the conversation. So I'm going to try and summarize some of the errors on this slide and misconceptions that are on this slide because I think it's kind of important. So we are ruled by calories. If you weigh this much, you can only have this many calories per day. And everything you eat has to have the number of calories written on it. Even if you get a bottle of water, it will say, this bottle of water has no calories in it. So how do you figure out what a calorie is? Well, you burn it. You take whatever it is and you burn it. And you burn it in a container that has water, and you see how much it raises the temperature of the water. So the definition of calorie is the amount of heat needed to raise the temperature of 1 gram of water by 1 degree Celsius. Okay? So here's where I have a problem with that. If you were to eat corn, all right, everybody just in your mind, go eat some corn. Okay, now wake up the next morning and go poop. What do you see in your poop? You see the corn. It passed through your body without being digested. A lot of it does. So corn is roughage. Roughage is stuff that burns just fine. So if you were going to get the calories by burning it, then you're going to get a lot of calories from corn. But when you actually eat it and run it through your body, most of it's going to exit in your poop without you getting any caloric value from it. So that's one of the things I have a little bit of a disagreement with them. The other thing is a calorie is actually 1,000 calories. So if I'm eating a candy bar and it says it's got 160 calories, multiply that by 1,000. And if it said it had 160,000 calories, you would be freaking out. So they just kind of leave the kilocalorie part off. And just, so it says it's 160 calories, but they put a capital C so that you know it's not a little calorie with a lowercase c. Like that. So if you go down here to the bottom of this slide and it says water is an effective coolant for every milliliter of perspiration. Well, 1 teaspoon is 5 milliliters. So a fifth of a teaspoon, if you had that on your forehead, it will remove 500 calories. You're like, whoa, man, I could eat like 3 candy bars at 160 calories. That's awesome. And all I have to do is sweat off a fifth of a teaspoon of sweat. I can do that. Well, no. These are little calories. Little calories. They're not kilocalories, which is what you're getting when you eat that candy bar or you drink that sugar sweetened Coke or whatever it is, cola that you're drinking. So it's they keep bouncing around with the little c and the big C, but that is 1,000 calories, not 1 calorie. So I wish we would stop that and then we would actually put kilocalories on the containers. Here's a few more terms that I want you guys to learn, especially A lot of you are going to go into nursing and you need to know the difference between a solution, a colloid, and a suspension. So let's do the easy one first. A colloid is going to be anything that's like jello. It's going to be thick. A solution is something that you've dissolved in water, or you've dissolved in alcohol, or you've dissolved in oil. You can have a solution where you've dissolved something, but it's going to be a liquid, usually. And it says the solute particles do not scatter light. So if I put pepper in a glass of water, it doesn't dissolve. I didn't make a solution. It isn't a solute. And where the water hits the pepper, it's going to bounce off. But in the case of where you've dissolved salt or sugar in the water and you have a solution, the water will pass, or the light will pass straight through without bouncing off. So it doesn't scatter lights. Most of the things that are in solution will pass through membranes, which is important because we need solutions to pass through our capillaries. We need it to pass through our lymph glands, which you don't even know you have lymph glands, most of you, but we'll learn about them and how stuff passes through them. Your kidneys, you definitely want the solutions to be able to pass through your kidneys so that you can pee out the toxic substances and maintain the good stuff that you don't want to pee out. The big thing is a solution will not separate out when you leave it out. So if I mix some sugar in my tea and then I come back the next day and taste the tea, it's still just as sweet. So it's not like all the sugar is dropped to the bottom, so the top is bitter and the bottom is sweet. It stays uniformly suspended. All right? And the opposite of that would be a suspension. So a lot of things that you get from the pharmacy, if it comes in liquid form, it says on the bottle, shake before using. If it says shake before using, you have a suspension. So over time, if you leave it sitting, the particles will drop out of solution. So it isn't a true solution, it is a suspension. So solution stays in solution, a suspension drops out over time. Gravity will pull it down to the bottom of the medicine bottle or wherever you have the suspension. So colloid, thick like jello, a solution dissolved and stays in solution, and a suspension eventually falls out of solution. But for a while, if you shake it up, then it's uniformly suspended. A classic example of a suspension is your own blood. If you draw your blood out and you leave it in a test tube and you come back, you're going to find plasma has floated to the top and the red blood cells and the white blood cells go down to the bottom. And so whenever you do this, we call this the hematocrit, and it tells you what percent you have of red blood cells and what percent you have of plasma. So it's one of those things that you have to keep in homeostasis. I was trying to think of an example of a colloid. They don't pass through membranes. They're too thick. They're too much like jello to be able to pass through membranes. And where would be a place where you'd want this? The one that comes to mind is your eye. You have fluid in your eye that's like jello, and you want it to be nice and thick like that. It holds the eyeball in shape, and you don't want that fluid to leak out. Or you don't want the fluid to leak in either, because then you have glaucoma. One kind of a suspension is also known as an emulsion. And an emulsion is where you take two things that won't dissolve and you shake them up. And oil and vinegar is the classic example. So you can shake it up, but within a minute or two, it's going to have separated out again. As opposed to a suspension may stay suspended for a couple of days before you have to shake it up again. So an emulsion is where you're mixing two things that are hydrophobic and hydrophilic, and they won't go together. But you can shake them up hard enough to make it a temporary emulsion. I'm going to pause here in this part 2, and I'll resume part 3 when we talk about pH. I'm spending a little more time in this chapter because I know a lot of you guys either haven't had chemistry or you had it so long ago that you've pretty much forgotten it. And you're going to need to know certain chemical things in order to understand the next chapters that we go through. So it's worth taking an extra hour, an extra lesson to make sure that you have the fundamentals of chemistry that you need. So I'll stop here and we'll come back with acids and bases in part 3.